In this video and the next one, I'm going to check Euclid's 5 postulates for hyperbolic geometry. Today we'll use what's formally known as the Poincare half-plane model of hyperbolic geometry. Mathematically, it's a bit messy and it involves more calculus than you might like, but the definition of length is very compelling. Then, in the next video, I will show you a model using a hyperboloid that will look much more similar to spherical geometry. So here's the setup. Hermes, messenger of the gods, has established a messenger service on a continent, and the shoreline is at y=0. Water here, land up here. Poseidon doesn't like this. He rules the ocean, as you know, where y is less than 0, but he can enchant the land, and he does it in such a way that the speed of a Hermes messenger is equal to y, the distance from the shoreline. Hermes has made a guarantee that when one of his messengers travels from point A to point B, it will take the route that requires the smallest travel time. But that route is no longer a straight line because travel is slow when we're closer to the water, fast when we're farther away from the water, and therefore it pays for the messenger to swing out into the region where travel is faster and then come back down closer to the shoreline at B. And remarkably, it turns out the path should be a circular arc with the circle centered at a point on the shoreline. So I'm now going to prove this. Here's how we do it. I specify the path of a messenger by giving the y-coordinate as a function of the x-coordinate. If you've studied calculus, you'll recall that the length of the path is obtained by taking 1 plus the derivative of y with respect to x squared, taking the square root of that and integrating it over x from x1 to x2. If you haven't studied calculus, you'll probably just want to tune out the next few slides because this is a slightly messy calculation. How are we going to calculate the travel time? Well, in order to convert distance to time, we have to divide by speed. So I take the same integral, but I put an extra factor of y in the denominator. And now the challenge is to find the path y of x that minimizes the travel time. Remarkably, this sort of problem was solved back in the 18th century by Euler and Lagrange, two of the great mathematicians of that century. This application of their technique dates to the late 19th century. And the basic idea of Euler and Lagrange is the same as for minimization problems in elementary calculus. If you have a variable and you want to find what value of that variable minimizes a certain quantity, what you do is say, well, I'm going to try adding or subtracting a little bit, and if I've got the minimum, nothing is going to change. So I'll set the derivative equal to 0. Here we're going to do the same thing. If we have the optimum path, y of x, that leads to the minimum time, and we tweak it by adding on a small multiple of any function that is 0 at the endpoints x1 and x2, thereby changing the path, the travel time shouldn't change. And therefore the derivative with respect to alpha should be 0 no matter what h of x I choose. Historically, this h of x is known as a variation of the path, and this branch of calculus, which is usually taught only in advanced courses, is known as calculus of variations. But we've got a single variable minimization problem. Having chosen h of x, we're just trying to minimize something with respect to the variable alpha. So we replace y of x by the modified path y of x plus alpha times h of x. And in the process, we also have to replace the derivative y prime of x by y prime of x plus alpha h prime of x. And now we insist that if we calculate the messenger's travel time for this tweaked path, where we've added on alpha h prime in the numerator and alpha h in the denominator, and we take the derivative of this function with respect to alpha, evaluate it at alpha equals 0 and set it equal to 0. If we can get 0 no matter what h of x we choose, we solve the problem. Okay, so we have to differentiate this with respect to h. This is about as messy an application of the chain rule as you will ever see. First, we've got an alpha here in the numerator, so we have to differentiate y prime plus alpha h prime with respect to alpha. That's going to give us a 2, which I will later cancel against a 1/2, and it's going to give us a factor of y prime plus alpha h prime. Then we have to differentiate the square root of what's under the square root sign. Since that's the plus 1/2 power, we're going to get the minus 1/2 power after we differentiate, and we get an extra factor of 1/2 that kills the 2. We also have in the denominator a y plus alpha h. But we also have to take into account the fact that there's a dependence on alpha in the denominator. Again, we multiply by the factor that's in the numerator. We have to take the derivative of the denominator with respect to alpha, which gives us an h of x, and we have to change the exponent from -1 to -2. So now this whole business has to equal 0, but it's not as bad as it looks, because we set alpha equal to 0 before we set the derivative equal to 0. So that term goes away, that term goes away. There's the first term. That goes away, that goes away, and there is the second term. Now one problem remains. We have both h of x and h prime of x. And this, I think, was really the cleverest idea that Euler and Lagrange had. We're going to get rid of this h prime of x by doing an integration by parts, in which we convert the h prime into h and convert the other factor into its derivative. So for integration by parts, we will say dv equals h prime of x dx, and u is everything else. There are two terms involving u and v at h1 and h2, but we're only considering variations for which h of x is 0 at those 2 points, so those terms go away. So what have we got? We have the first term now gives an h of x, which I'll take outside the parentheses, and then from du we have minus the derivative with respect to x of y prime over the square root of 1 plus y prime squared times y. So this whole business equals 0. For what values of h of x? For any continuous function h of x. And the only way that can happen is that the quantity multiplying h of x has to be 0. So I set this equal to 0, and what have I done? I've taken an unsolvable minimization problem and traded it in for an unsolvable differential equation problem. This is a differential equation because it involves derivatives of the function y. Now I confess I don't know how I would stumble across the solution to this differential equation if I didn't already know it. But I do already know it, so I'm just going to plug it in and show that it works. And by the way, if you are doing the concentration credit version of this course, this is the second of 8 proofs out of which you're going to have to do 6. So if you can master this messy calculus, you've got 1/3 of your concentration credit already in the bank. Okay, what's the solution? It's a circular arc. I'll call its radius capital R, and the center is somewhere on the shoreline. Y equals 0, and x has some arbitrary value, x naught. So y squared plus x minus x naught squared equals r squared. And if I differentiate this with respect to x, I get 2y prime from the first term. And differentiating the second term with respect to x, I get 2 times x minus x naught. So that has to be true for this circle. And now I can solve for y prime, calculate 1 plus y prime squared. So that'll give me 1 plus this squared over that squared. And when I put everything over the common denominator and use the equation for the circle, I discover that 1 plus y prime squared equals y squared, r squared over y squared. Okay, let me quickly review what we just found. We just found that 1 plus y prime squared equals r squared over y squared. So the square root of 1 plus y prime squared is just r over y. Now I take the equation 1 plus y prime squared equals r over y. When I differentiate the left-hand side, I get 2 times y prime times y double prime. When I differentiate the right-hand side, I get minus 2 y prime over y cubed times r squared. Sorry, I was differentiating this. So that's where the r squared comes from. And it's differentiating 1 over y squared with respect to x that gives me minus 2y prime over r cubed. Cancel out the y primes, and I find a formula for the second derivative of y. It's minus r squared over y cubed. Now let's go back to the original equation that we were trying to solve. On the right-hand side, I get rid of the square root by replacing 1 plus y prime squared plus r over y. So this turns into just minus r over y cubed. On the left-hand side, I look at the denominator and say, hey, that looks like a function of x, but it's not. It has the constant value r, so I only have to differentiate y prime over r. That gives me y double prime over r. Now let me make some use of this equation, and we will be done. What we have found, let's look back here, is that when we differentiate the equation for the circle, we find y prime equals minus r squared over y cubed, and therefore we have verified that we have found a solution to this differential equation. A Hermes messenger should move along the Euclidean semicircle that passes through the start point and the end point, and that has its center on the shoreline. There is a unique such circle. The only case where we can't find such a circle if the start point and end point A and B have the same x-coordinate. In that case, the solution is just a straight line perpendicular to the shore. Okay, messy calculus over. Now we can do some geometry with it. So here are 2 points A and B between which a Hermes messenger travels. The hyperbolic line through A and B is this semicircle, and it qualifies as a line because while it doesn't give the shortest distance between 2 points, it gives the shortest travel time between the 2 points. And how do we construct this? That's quite easy. Form the segment AB, construct its perpendicular bisector. The place where it intersects the shoreline is the center of the circle, and then we just draw a circle centered on x naught, passing through A, also passing through B. Now let's see if we can get the formula for hyperbolic distance, the formula for the travel time. And all we have to do is consider the special case where the circle is centered at x equals 0. And we just have to calculate the time for the messenger to travel from the point directly above that to a point where the x-coordinate has increased to x1 and the y-coordinate, since we're on a circle, has dropped to the square root of r squared minus x1 squared. So the travel time is given by this integral, but we found that that was equal to r over y squared. And since we're on a circle where x squared plus y squared equals r squared, we can replace y squared by r squared minus x squared. In elementary calculus, this is done by the method of partial fractions, though you might say, hey, didn't we do that in class 2? Doesn't this turn out to be an inverse hyperbolic tangent function? Well, yes, it does, but let's do it in the standard way. We write 1 over r squared minus x squared is, or r over r squared minus x squared is 1/2 1 over r plus x plus 1 over r minus x. Both these things are easily integrated. They turn into logarithms. The difference of logarithms is the logarithm of the quotient. So we get 1/2 log of 1 plus x1 over r over 1 minus x1 over r. And if you're really eagle-eyed and have a memory like an elephant, you say, hey, isn't that another way of writing the inverse hyperbolic tangent function? Well, it is, but we're going to rediscover this. I'll invert this function by solving for x1 in terms of t, and what I find is that x equals r times the hyperbolic tangent of t. In other words, the distance horizontally that a Hermes messenger travels is proportional to the hyperbolic tangent of the travel time. So here I have labeled the points that the messenger will reach after traveling a certain hyperbolic distance. That is, after traveling for a certain amount of time. If the messenger goes along the circle, as the messenger gets closer and closer to the shoreline, the hyperbolic distance from the starting point gets larger and larger. Never reach the shoreline. Since the messenger travels faster, where y is large than where it's small, it's not surprising that the messenger will get farther traveling north than traveling south. Now let's see if we can figure out something about circles in hyperbolic geometry. I'm just going to state, not prove, the really interesting result. But let's look at north-south travel. The messenger starts where y equals r, moves along a straight line perpendicular to the shoreline, and the travel time is obtained by integrating dy over y from r to y1. That gives us the log of y1 over r. And if we solve this for r in terms of t, we find that the distance increases exponentially with travel time. Going south, the y-coordinate is r times e to the minus t. That's nice. It means that as t approaches infinity, the messenger is just reaching the shoreline at y equals 0. Now it turns out that The hyperbolic circle, that is, the points that the messenger can reach in time t, is also a Euclidean circle, only the Euclidean center of the circle is not the same as the hyperbolic center of the circle. So, where's the Euclidean center? It's at the middle point between the northernmost point and the southernmost point. 1/2 of e to the t plus e to the minus t. So it's at y equals cosh t. And the radius must therefore be e to the t minus the center, which is at cosh t. And that difference is conveniently equal to the hyperbolic sine of t. Suppose the messenger heads off in an easterly direction and swings around to reach the coastline. Well, after traveling for time t, the messenger will be at a point whose x-coordinate is the hyperbolic tangent, whose y-coordinate is the hyperbolic secant, and if I calculate the distance r from the point that I've labeled M in the diagram, I get difference in x-coordinates squared plus difference in y-coordinates squared. If I put everything over a common denominator, then this turns into 1 minus 1 over cosh squared t, which is the hyperbolic tangent of t, and I find that I have, sorry, I said that wrong, 1 minus the hyperbolic secant, which is the hyperbolic sine. So I have sinh squared minus sinh fourth. I factor out 1 plus sinh squared t. That cancels the cosh t. And I find the distance from the center is the square of the hyperbolic sine, just as it was for this point and for that point. Finally, we can check the postulates. I've shown you how, given any two distinct points, I can construct the unique line of hyperbolic geometry along which a Hermes messenger will travel to get from point A to point B. So postulate 1 is okay. Given a hyperbolic line segment, an arc of one of these circles, I can extend the circle all the way around to the shoreline on either side, and since that's an infinite hyperbolic distance, I can extend it as far as I like. No exception, as we had in spherical geometry. If you give me a point and a radius, that is a travel time for a hyperbolic circle, I can do the same thing I did in spherical geometry. On any line through P, I can construct a pair of points that a messenger will reach after traveling in time equal to the radius of the circle. The set of all such points satisfies Euclid's definition for a circle, so it's a hyperbolic circle. Finally, it turns out, though I haven't proved it, that the angle between two hyperbolic rays is equal to the Euclidean angle between the rays, that is, between the lines tangents to the rays. So if two semicircles cross at a right angle, they determine a right angle in hyperbolic geometry, and that means that right angles exist in hyperbolic geometry. Euclid's fourth postulate says that any two right angles are congruent. In order to prove that, I'd have to specify the group of length-preserving transformations in hyperbolic geometry, which is above my pay grade. So what goes wrong? Well, in Euclidean geometry, it's unusual for two lines to fail to intersect. That's the special case of parallel lines. In hyperbolic geometry, as I will now show you, two lines often fail to intersect. And here is one of many examples. line A makes a right angle with this vertical line. Line B actually makes an angle that's less than a right angle. And Euclid says if this angle plus this angle is less than two right angles, then these lines will intersect on this side. But they don't. They never reach the water, and they don't intersect. So the fifth postulate fails in hyperbolic geometry. Let me conclude with a brief comment about equilateral triangles. In Euclidean geometry, it's easy to spot an equilateral triangle. And on a sphere, it's also easy to spot an equilateral triangle. But in this model for hyperbolic geometry, it's very difficult to identify an equilateral triangle because we cannot tell by sight when two hyperbolic lines are equal in length, and it's tricky to spot the fact that all three angles are equal because, as you'll learn later, they're not 60-degree angles. However, Euclid has a construction that uses the first four postulates, and the proof of that construction is valid also in hyperbolic geometry. We just trade our compass in for the circle drawing tools that are built into R. Similarly, proposition 2 in Euclid says how I can construct at a given point a line segment that has the same length as some other specified segment. In Euclidean geometry, we could cheat by using a ruler or a pair of dividers. No such cheat exists in hyperbolic geometry, but Euclid's proof of proposition 2, which involves drawing various circles and constructing an equilateral triangle, will still work. When I do all this in R, you'll see in more detail how these constructions come out. And I would say if you are well versed in calculus, you should try to master some of the messy calculations in this topic. If, however, you've never studied calculus, just pick up the basic ideas about how Euclid's postulates are satisfied in hyperbolic geometry, all but the fifth one, and you'll be well off.